This is going to be your intro to static equilibrium, which is Newton's first law: an object at rest wants to stay at rest. And this occurs when the forces are balanced, or you'll hear me say the net force equals zero, the sum of the force, all the forces added up. First, let's look real quick at a PhET simulation. So it's all about a tug-of-war game where nobody wins. So if you go into this, you can play around with some scenarios on your own. But I'm just going to do some real simple ones. If I put one of these little red people to the right side, you can see that it shows their rightward force above the bin that they're playing tug-of-war over. If I press play, this will be unbalanced and it's going to actually accelerate, which we don't want. So the game is, if I have a rightward force of this amount, which you could see the values if you want to check that in the little box there, 50 newtons to the right, we need to have that countered with a 50 Newton force to the left. If I hit go, of course nobody wins, and this is static equilibrium, an object at rest stays at rest. Reset this, I could do this with other scenarios, so we could pick one of the medium-sized people here. Again, right force right now is kind of vague, so if I put the value with it, 100 newtons. I could counter this with, of course, this person, although I could actually do it with two 50 Newton forces pulling to the left. Again, as long as they basically add up to zero, so being mindful to the right is positive, to the left is negative, hit go, you have static equilibrium. All right. So this right now is limited to just one dimension. We're in the X dimension right now, and this is about as simple as it gets. Okay. What we're going to do in the lab is we're going to play this tug-of-war game, but we're going to do it with hanging masses, or if you think about it, a mass in the gravitational field, that negative 9.8 number, that actually creates a gravitational force, or what we call weight. So the setup you're going to use in the lab is shown up here in the top right. I call it the force table. And you're actually going to be able to hang masses and use their weights to play tug-of-war. This right here is a picture of the force table from above. So you can see that it'll do a 0 to 360 degrees all the way around it. And we're going to call pretty much this 0 degrees and 180 degrees. We're going to call this the X dimension, shown right here. And the 90 and 270 is going to be, of course, our Y dimension. All right, so we'll use that as a guide to what we've done before with vectors, because forces, are still vectors. So I'm going to do a couple of these for you guys. It might drag out a little bit, but it's going to help you out with the lab so much. So the table down here is actually what we want to look at. All right. So the idea is we're trying to, of course, hang these masses. I'm going to give you two of them that you're going to hang, call it mass A and mass B. And you're going to try to figure out the third mass that needs to be hung and at what angle or what direction to balance it all out. All right, first thing though, mass is not a vector. Mass is a scalar. It's just the amount of matter or stuff something's made up. So I've got to apply this as a force. And if you think about it, if we do hang this mass, it's going to have a weight. So we're going to use the Fg equals m times g. Remember though, mass needs to be in kilograms. So if I do the first one, for instance, for you guys, that would be divided by 1,000 to get it to kilograms. So it'd be 0.025 kilograms is the equivalent of 25 grams. And I'm going to multiply that by negative 9.8, but I give you a little hint, just do the absolute value of this right now to make it easy. All right, we'll just do it as negative 9.8 meters per second squared. And this will give me a gravitational force of 0.245 newtons. Now, yes, this does pull down on the hanging mass, but if you kind of look up here at the setup, what we're really looking at is this string that's connected to the weight of the object. We're looking at that pulling on top of the force table. All right, so let me erase this work, but put my data down here. So you'll be a lot cleaner with your work than I'm sure I am. I'm pretty blown up right now. All right, but we just found out the weight of this 25 gram mass, and here comes the next big thing. It is a vector, so it has a direction as well. So if I look at the angle on the force table, you can see that the angle is 0 degrees, and that's over here. So I'm going to draw this force to the right, the positive x direction, and basically just say, hey, the force from mass A is in this direction with a value of 0.245 newtons. All right, we're going to do the exact same thing for mass B, which you would repeat that same equation. What I end up getting for this is 0.441 newtons, but you look at the angle, it's 180 degrees, so this is actually to the left, and it is larger than the 0.245, so I'm going to draw it a bit larger and call it force B. All right, you could even add that this is in the negative x if you really wanted to give yourself some little details. All right, but right now these are the two forces that will be pulling on this ring in the middle of the force table. You'll see it when you get the labs, but it's like a little ring, and you want it to stay balanced in the center. Well, if these are the only two forces, that's not going to stay balanced. So the idea is, what general direction does the third force need to pull? And then I want you to calculate the exact amount. All right, so if I kind of approximate just with this picture, it looks like I need another force helping this to the right. How much, I don't really know right now, but let's just call it force C, and that's what we're trying to find. All right, this table down here right now, it's probably a little more than it needs to be, but I'm trying to help you for future forces that are at angles. The idea is that all of this 0.245, right now if it's at 0 degrees, it's all in the x. So there's no component breakdown needed. It is then just 0.245 newtons in the, though, positive x. So see how I already helped you out with it's in the positive direction because it's 0 degrees on the table. Same thing then with the 0.441 newtons. It's 180 degrees, so you can see I've already actually put the negative there. I'm going to go over it just so you can see it very obvious. Okay? The big idea then is right here. So this is called Newton's first law, and I've already set it up for you for this problem. So here's the huge idea, and it essentially says if your object's at rest staying at rest, it's not accelerating, so all the forces better add up to 0. The only forces we're dealing with are in the x dimension, so you can see I just called them FA, FB, and then the unknown FC. So since I've set up the law for you, you just need to continue it and say, all right, FA is positive 0.245 newtons, plus FB is negative 0.441 newtons, plus FC is that third force that's going to balance it out and have everything add up to 0. So it's just your simple math right now. If you solve this out, oops, sorry, I'm a little glitchy there. If you solve this out, you're going to get that that third force is going to be positive, because it does need to actually help out mass A and its weight pulling to the right, positive 0.196 newtons. All right, so I would put down here positive 0.196 newtons is the force that's going to balance out the x, and it's only in the x right now, so I don't need to do anything in the y. So the positive means it needs to be at an angle, of 0 degrees, all right, because that's the positive x, and all of its value is going to be in the x. So that's just the absolute value, ignoring the direction. The last thing is the mass. So remember, this is not a mass, this is a weight of what's hanging. So we need to use that one equation again, Fg equals m times g. We need to actually take this and apply it to the weight right there and divide by negative 9.8. Don't worry so much about the negatives right now. This force is hanging off the edge of the table. So when we're not on top of the table like this, the weight that's hanging here technically is pulling in the negative direction of space. All right, don't overthink that though, just trust me. We're gonna take 0.196 divided by 9.8, just cheat it and make it positive for now. And I'm then gonna get, let's erase this real quick and make it all pretty. I'm gonna get 0.02, but that's kilograms. So I want to actually convert this to grams, so that ends up being 20 grams. So what you're gonna do is then when you have this mass predicted and you know the angle it needs to hang at, you're gonna set up this force table with all three masses hung at the appropriate angle. And then if it balances out, the ring in the middle right here it won't move left, right, up, or down. It'll stay perfectly in the middle, and then you'll call me over and I'll check it and I'll sign it off for you guys. All right. So you're going to do this for other ones as well. I think right now, so I don't talk your ear off, I'll kind of not solve every little detail, but show you the gist of the next one. So part 2, you can see we're going to hang masses. You can calculate their weights, which equate to the force. But this one's 0 degrees and this one's 90. All right, so just to give you a general idea right now, the 0 degree is going to pull to the right. Call that the force from mass A. And the 90 degree is going to pull up. And that's the force from mass B. If I want to make a quick approximation, I already know that it should actually pull so that it counters both of those. Because I got to counter this rightward with a leftward pull and the upward with a downward pull. How do you solve for this? Well, we're in 2 dimensions now. So you can see I've actually set up Newton's first law on the x to where FCX, if I want to draw components, FCX is going to balance out FA. And then I also had to set up in the y where FCY is going to balance out FB. If I can solve for FCX and FCY, I can then use this triangle with the components to solve the total force from FC. All right, do your basic trig right there with Pythag, and keep in mind, I will want a direction as well. So if I calculate this angle, which is south of the west direction, I can work it all the way from 0 over here and be like, all right, this is 90, this is 180, and then I can add the remaining angle to that 180, and that would then be the angle I can put down here in my data table. Same idea as before. When you get the force in the x, the force in the y, you get the total with Pythag, and then you can do that Fg equals m times g equation to get the mass once you convert to grams. Again, set it up. All right, if your math looks good and the force table is all balanced, I'll come by and give you a signature on that, okay? All right, you're then going to see part 3 is very similar. The only difference is they won't be the same mass hanging. The 90 degree will be 45 grams, so it might not split the third force evenly. But then you'll get to the last parts, all right, where you could have a force at an angle like this. So just be mindful, if I have my first force A to the right, nothing crazy there. All right, but I have my second force B at 120 degrees. All right, do the best I can with the drawing. And that's not really to scale with the other one, so I would want to fix that. We know that any vector at an angle, you have to break it down into its components. So before I can even set up Newton's first law in each dimension, I need to actually take this triangle to the side. So you can see I did space right here. I need to take this vector that's at an angle, and I need to break it down into its components. So I might actually scoot it over a little bit because I'm measuring it from the y-axis because it's at 120. So this right here, it's not 120, that's actually 30 because I'm going from 90 to 120. All right. If I, of course, am able to break down this force of B into its components, I can show that work right here with trig. And then when I do set up Newton's first law, I'll do one of them for you. This would be the force A, because it's all in the x. This would not be all of B, but just the x value. And then there's going to have to be some x direction pull of C to balance it all out. Okay? Same thing would apply for the y, except FA doesn't have any magnitude in the y, so I wouldn't even put FA. I would just put, you know what, FB has some y pull that I can find out with my component breakdown, and FC really just needs to cancel that, so FCY is the only other force. When I do find these x and y values of the third unknown force C, I can then come down here and do my tip to tail to find the total force that C needs to pull with. Again, it's probably approximating. It's probably got to pull, I don't know, a little bit more to the left, it looks like, than down. So it's probably got to pull this way. Oop, you know what? Actually, I'm wrong. B is actually helping cancel out A. So it's actually got to pull down a little bit this way, I think. All right, and if you don't feel confident, if you second guess yourself like I did, that's okay. The math is more foolproof. All right, so hope this helps. If you want to go ahead and try a couple of these coming into the lab, I think that might save a little bit of time and stress while you're in the classroom and leave more time for questions and confirmation. But no need to complete the whole lab with the predictions, just do a few, okay? All right, hope this helps. Best